Welcome to In Plain English, a podcast where we discuss scientific research in terms that are accessible to everyone, not just the experts. I'm your host, Jamie Moffa. Before we get started with today's episode, a few reminders. You can download the paper for each episode at inplainenglishpod.org by clicking on the episodes link in the main menu. You can also listen to previous episodes there. We believe in open access science for all, so the papers we choose will always be free for you to download. If you have a question or comment about a previous article, you can submit it under the Continue the Conversation tab. In future episodes, we will begin by reading and responding to some of the questions and comments that you send in. If you are interested in being a guest or presenter for a future episode, you can click on the Become a Guest tab on the website. You can also reach out to us on Facebook or Twitter at Plain English Sci. That's PLAINENGLISHSCI. To listen to this podcast, you can find us on Google Podcasts, Spotify, SoundCloud, or wherever you listen to podcasts. With that out of the way, on to today's paper. On today's episode, we'll be talking about astronomy, and this month's paper is titled How Much Water Was Delivered from the Asteroid Belt to the Earth After Its Formation. Presenting this paper is Will Saunders. Will, would you like to introduce yourself?
Absolutely. My name is Will Saunders, and I am a fourth-year PhD student in the astronomy department at Boston University. My specialty is in the atmospheres of planets in the solar system, but specifically, I study the atmospheres of Uranus and Neptune right now. And I'm really excited to be on the show. Thanks for having me, Jamie.
Cool, thanks for being on. And joining Will for this discussion are our two guests for this episode, Nick Woolslegel and India Bland. Nick, India, would you like to each briefly introduce yourselves?
Sure. My name's Nicholas Woolslegel. I have a piece of paper calling myself a chemical engineer, and I've got a long history of enjoying pop science and an even longer history of staying away from hard science. So I guess my goal from today is to change that second fact.
Hi, I'm India Bland. I'm a junior at WashU, and I'm studying philosophy, neuroscience, and psychology, and minoring in AFAS, or African American Studies.
Great. So without further ado, Will, take it away.
All right. I'm excited about this paper. And I think before we jump into the science, I just want to briefly give an overview on why I chose this paper. I think, first of all, the title is so great. Being a full sentence and a question, just that always speaks to me. It's very clear what they're doing. It's also in plain English. There's no jargon in the title, which you love to see. But this paper also has a lot of topics. So we're going to get into a lot of fun introductory material before we get to the actual study itself. And I think that's a great reason to pick this one. And then it's also nice and short and well written. So I think it makes a great paper that you can pretty much pick up and read without too much trouble. So enough premise, let's do some of the science background. Now, on Earth, we have, as a species, an intimate connection with water. I'm drinking a glass of water as we record. We all rinse ourselves in water nearly daily. It's part of life, and it's everywhere. But in fact, that's not true for most of the other planets in the inner solar system. There's almost no water to speak of. And in fact, you might be surprised to learn that geologists estimate Earth has somewhere between 1 and 10 oceans of water. That is, there could be 9 times more water underground than all the water in the oceans that we know about. How is that possible? Where is this water, this mysterious, these oceans of water? And it turns out that the most likely place it could be is in the mantle. The mantle is the middle region of Earth, and it is solid. It's made of rock, the components of which would be familiar to us, but there's nothing familiar about the mantle at all from our experience. It is incredibly hot, and even more importantly, incredibly high pressure. And what that means is the entire physics of how rock behaves under those circumstances differs from everything we think we know about rock. It's really more like an incredibly thick liquid than a hard solid. So where is this water stored underground in the mantle? It's actually not even water. It's the constituents of water But what happens when you get H2O under extremely high pressure and temperature is the H and an OH separate, they dissociate and dissolve into the rock. And this happens in one of the most common types of rocks, which is olivine. This is a mineral that's incredibly common on the surface and in the mantle. And when water dissolves and bonds into it, it forms two rather funny sounding minerals. It's wadsleyite, wadsleyite. There's an L in there I don't like. Wadsleyite and ringwoodite. So, I mean, these are ridiculous and mysterious compounds, but they literally contain oceans and oceans of water stored thousands of kilometers under our feet. And so there's a narrow sort of a band in the mantle where the pressure and the temperature change in such a way to make the formation of wadsleyite and ringwoodite stable. And so that's sort of the underground water reservoir, though it's not really water. It is, in theory, water, because if you brought it up to the surface, it could return into liquid water as we know it, though it's not stored in that form.
I find it absolutely crazy that you can say there's water in the earth, and it's really the components of water at that point. Water is broken down, water is split up. You don't have H2O sitting around, but it's ridiculous to think that there's a stockpile of the ingredients to make water in the core of our planet that just got there at some point.
It's pretty wild. I was shocked to learn this not that long ago, in fact. As I said, water is a very common thing on Earth's surface, turns out even more common underground, but incredibly uncommon in the inner solar system. Mercury doesn't have any atmosphere, really. In fact, Mercury doesn't even have a mantle to speak of. And so there's no chance of having water anywhere on Mercury. Venus has an incredibly thick atmosphere, about 100 times thicker than Earth's, but it's too hot for liquid water to exist on the surface. And so Venus, if it ever had water, has lost it. Mars today has a really thin atmosphere, not enough pressure to make liquid water stable, and only has a little bit of ice near the north and south poles. So it's possible Mars could have, and this was actually a cool paper that I covered for Astrobites a while back, could have these briny salt puddles that sort of come into existence, could reanimate some dormant life and then kind of dry up again, which is a kind of a ridiculous possibility, but it isn't completely out of the question. Though billions of years ago, Mars could have had, likely had, some would say, global oceans, and the atmosphere was much thicker. But Mars's atmosphere was gradually lost. And so as the pressure decreased, the oceans of water would have, quote, boiled off, leaving behind the dry, rusted landscape that we see on Mars today.
I just want to stop you there. That is crazy cool. What's evidence or theory or what information do we have that implies that Mars had a thicker atmosphere in the past?
Yeah, that's a great question. So there is some pretty decent evidence if you look at how the solar system formed. So when a planetary system forms, this is true for our solar system or any around another star, you have the protostar, the young star at the center, and this envelope or maybe a pancake-shaped disk of gas and dust. And so it's all swirling around, coalescing, and gravitationally clumps and gets bigger. How exactly you form planets is still a huge open question in this field. But one thing is for sure, the environment is about the same for all of the planets in the inner solar system when they formed. You have to assume they all had exposure to the same elements from this primordial envelope of gas and dust. So the differentiation had to happen after they formed. And the reality is that Mars is probably too light. It's probably not massive enough to hold in air. And so the atmosphere was puffier than Earth always. And because it was puffier, it could get hit by high energetic particles and gradually lost to space via processes that could take billions of years, but there were billions of years for it to happen. Another way of thinking about it is looking at the surface of Mars. there are sort of channels in the surface of Mars that very likely could have been carved by water. In fact, I did attend a talk a couple of years ago on this Mars conference that very, very vehemently tried to argue that you could get certain types of channels on Mars via dry formations, so kind of like a rock slide instead of a river. There were a lot of skeptics in the audience, and that was an interesting talk to listen to because of the debate going on. But well, I'll say most astronomers, most planetary scientists believe that they can only be formed from water. And so if Mars had liquid water, it had to have a much thicker atmosphere in order to increase the pressure. Great question, though.
I was also curious about what you were saying earlier about like how Venus is too hot for water to exist. I feel like the mantle in the Earth is also like super hot. So how do you, I don't know how like the temperatures like compare, but how is one able to exist without the other, but not the other?
That is a really great question. It's not just the temperature, it's the pressure that is changing the environment in the mantle. So the temperature keeps going up and the pressure goes up a lot too. And at a certain point, the nature of what rock is and the nature of what water is begin to change. And that's why it's not really water, as Nick summarized correctly. It's the components of water could be reconstituted into liquid water under the right circumstances. It's dissolved. It's like when you put sugar in a glass of water, you know there's sugar in there. You can taste it. It's definitely sugar, but you can't identify it. You can't point to it and say, there it is. But if you evaporate out all the water, eventually the sugar will sit at the bottom of the glass. So it's kind of like that. You don't recognize it when it's in that form. Venus on the surface, so underground, we could have the same situation on Venus. No one really knows. We don't have evidence of that. But the surface, the temperature kind of outpaces the pressure. So it's not hot enough and pressure enough to create the forms of water that would lock it into the rock. So if you put liquid water on the surface of Venus, it would just like immediately evaporate and end up in the atmosphere and then eventually get lost into space. Well, the hydrogens would get lost into space and the oxygens are a little heavier, so they might stick around for a while because there's a lot of CO2. It's possible that's where some of the O2 to make the CO2 came from water where the hydrogens were lost.
So it's kind of like how with a pressure cooker, you can raise the temperature of water beyond its normal, quote unquote, boiling point, except you're raising the pressure so high that you're no longer even talking about water as a liquid. You're talking about it as, well, not just a solid either, but something closer to that.
Yes, I think that's a great analogy. I agree.
Crazy.
Yeah, it's pretty crazy. It certainly breaks whatever conception you had of what water is and what rock is.
But we think that there is between 1 and 10 times the surface quantity of water, the total amount of water we have on the surface of the Earth, between 1 and 10 times that exists beneath the surface. I guess the next question, and I know the paper gets into this, but I'd like to ask you is, how does it get there? How did it get here?
Yeah, well, so I'll answer the easy part first. If you had water on the surface when the Earth was still largely molten, so there was enough magma on the surface and kind of recirculating into the interior of the Earth, it could have been sort of captured or dissolved into the magma and brought down, maybe even as vapor. It was sort of captured into bubbles and brought down until the pressure got high enough where it could do this dissociating thing. So if it's on the surface, that's how it gets underneath. The question of how it got to the surface, now that's the whole point of the paper. So to answer that question, let's turn to where could water have come from? Well, so there are a bunch of interesting theories. It's possible that Earth could have formed with the constituents of water. I don't think many people believe this is possible because it would kind of change what we believe these pancakes of dust and gas are filled with. And the circumstances of the Earth right as it's forming, because this is the very, very beginning of the Earth, we're too turbulent and too unstable for any sort of water to be part of that system. Just too hot. So probably not that one. There was this belief that you could have liquid water delivered from somewhere else in the solar system. The problem is Earth is too close to the sun, has always been too close to the sun to have liquid water, if not for the high pressure. So if you bring water out into space, eventually it'll just freeze, but before that it'll actually boil because the pressure will get to it first. It'll boil until it's spread out into nothing, and then the little crystals will freeze. So you can't bring liquid water could never have a chance of coming to Earth. Couldn't even come as solid water because as soon as it got close, it would sublimate, go directly from solid to gas and be blown off whatever rock was bringing it in. So if water is being delivered to Earth, it has to be delivered in the same kind of dissolved solid form as is currently in the mantle. Not exactly the same, different types of rock, different types of formation, but it has to come from what is mostly rock with a little bit of these water parts and be delivered by impacts, little by little from somewhere where it's colder in the outer solar system over probably tens of millions of years via some series of small and large impacts.
Quick question. You say for the water to be delivered, and this is already blowing my mind from what I read in the paper, it had to be in that mineral form that we see in the Earth. I've heard all my life about water-rich asteroids and meteorites, and maybe not meteorites, but water-rich objects from out beyond, in this paper, they say it's like the ice zone or whatever, going by the sun and creating these amazing comet trails and that sort of thing. Is that actually mineral water and not frozen water, or are there frozen water comets out there too?
Great question. Most comets are actually made of ice, frozen water.
Okay.
They're not this mineral water. They're called like dirty snowballs, and that's really an accurate description. So when the comets start to move closer to the sun, they develop that tail pointing away from the sun. That is mostly sublimated ice, turning directly from ice into vapor. So if it were to be comets delivering the water to Earth in the form of ice, the problem is the ice wouldn't make it. It would mostly get sublimated away and the vapor would be out in space and lost. So that's why it's got to be delivered as something more solid, because Earth is too close to the sun for the comets to get close enough.
Makes perfect sense.
Yeah. Pretty crazy stuff though, because there's not a ton of water. I mean, the comets are mostly water. These rocks are not mostly water. So it would take a lot of impacts to deliver enough water. As a fun aside, it turns out collisions in the solar system are one of the most common things. And even giant impacts explain a lot of things that we don't have great explanations for. Sometimes they're not the best explanation, they're just a explanation. Though I think a lot of people have an affinity for these giant collisions. For example, I mentioned briefly earlier that Mercury has no mantle. A leading theory on a paper that I covered a while back says that Mercury was hit with a giant impact that knocked its mantle away, and it lost gradually these mantle particles that were, because it's so close to the sun hits it so hard that it just got gradually blown away. And now it's just like lithosphere, that's crust, and core, and there's almost no mantle. Venus is almost spinning exactly backward from every other planet in the solar system. People are like, no, maybe that was a giant impact, right? The Earth likely had a giant impact to form the moon, though there is some new research that suggests it doesn't have to be one giant impact, maybe a few smaller, though still massive, though not quite as massive, impacts that could do the same thing. As we all know, Uranus is the funky planet that spins on its side. Why not? That is perfect candidate for a giant impact to knock it sideways. Anyway, it's just, people love these giant impact theories. They're great to model. They explain a lot, and it's hard to disprove them. So they stick around for a while.
It sounds like you're pretty skeptical of giant impact theories though.
Yeah, I'm a little skeptical.
So you said that Mercury doesn't have a mantle, just crust and core, and there's
a little bit of a mantle.
Okay, but it's just, is there no tectonic activity on Mercury? Is it just crust sitting on it? How do you cut out the middle layer of a planet and then leave everything else?
Right. Well, it would have to have lost a lot of crust as well, and then the crust kind of redevelops So that can happen in a number of different ways, but Mercury has no internal engine. There's no heat source internal. So it's just cooling. And as it cools, eventually all of the mantle will cool down and kind of just become more and more crust. But no, it's not tectonically active. Mars is not tectonically active. We believe Venus is not, but it totally could be. So moving on, the goal of this paper is to test whether or not there would be enough collisions of material, asteroids from the outer solar system that could deliver water to the Earth to account for up to 10 oceans of water. Most of these asteroids that they care about come from anywhere around the asteroid belt or even a little bit further out. So we're not talking the far, far outer solar system. We're talking the middle solar system, I guess. So that's not really a technical term. And the way that they looked to simulate whether or not this could have happened when the solar system was forming is something called an N-body simulation. This is a very common type of simulation used in planetary science. If you took an advanced physics or astronomy class, you might have solved the two-body problem, which is a really famous problem where you have two objects in orbit around their common center of mass. That's a hard problem. It's a lot of work. It may even take a few days of lecture and pages of notes. And then once you try to go up to three bodies, you can't even solve it. It becomes unsolvable right then and there. A computer could solve it, but there's no closed form solution. You can't write on the board what the solution is. The computer just keeps calculating using numerical methods and will give you a result at a time if you ask for it. So that idea is extrapolated up to n bodies, as many bodies as you want in this problem. And the way it works is the computer at any moment in time keeps track of all the particles and computes the gravitational forces acting on each particle by every other particle. So it picks the first particle, goes to the second particle, how much gravity pulls on that, third particle, how much gravity pulls on that, all the way down. And then does that again for every other particle. Takes a ton of computing power to do this. It sees how much force is in each direction for each particle, and then steps forward in time. The particles move based on Newton's second law, F equals ma, and the forces that were calculated. And then the computer does it again. Okay, now they're in a new position. Figure out what their gravitational forces are, and then we'll step forward in time. You can do time steps in a second or maybe 100,000 years. So the N-body simulation is tailored to the complexity and the duration that you're interested in studying. And you can also decide how complex you want it to be. In this paper, the authors built a simulation that included the Sun, Earth, Jupiter, Saturn, and the asteroid belt. That's it. They didn't want other planets. They didn't want other things going on because it probably didn't matter, and it would just take computing time that would inhibit their ability to actually test the thing that they were excited about. Another interesting assumption they made is that the asteroids in the simulation are test particles, which means they don't interact with each other. And that's kind of weird to think about because, of course, asteroids should be able to collide. But it turns out they actually don't collide as much as you would think. So it's pretty accurate to do an N-body simulation where the small bodies are test particles and could even pass through each other. It doesn't change things that much.
Not to mention the fact that an asteroid hitting another asteroid might have an effect for that asteroid. Like it probably isn't happy that it just hit someone else, but it's not going to have as serious of an effect as the long pull of its orbit around the sun or its orbit around Jupiter. Like a car crash on the highway isn't anything like the gravitational pull of a planet pulling you in one direction.
That's true. And it could end up just making a series of asteroids instead of one or two asteroids that all end up going the same direction anyway. So you don't want to waste computing power keeping track of more than you have to.
Not to get too in the weeds about computing power, a huge amount, at least from simulations I've run back in undergrad, a huge amount of the accuracy does depend on your time iteration. So you mentioned that you iterate by time. So your test particles are in one position with forces acting on them. And then one time step later, they're in a new position with the summation of all those forces having changed their position.
Yes.
Well, if you have a time stop of, and you generally want to have like the largest time interval that makes sense without affecting results, because the more granular you're iterating, the smaller iterations you make, the more calculations you have to do. And you can end up having a calculation that runs forever to just simulate 1 day of gravitational force or whatever it is you're simulating. But if you make too big of a time jump, your calculation gets less and less accurate, because let's say you're calculating the position of asteroids in this field 1 day later, after assuming all the forces they have on them stay constant. Well, for 1 day, that's probably pretty reasonable. Your asteroids will move in whatever direction the summation of their forces move them in, and then new forces will take effect. But if you are, let's say you're running an experiment that lasts millions of years, like they do in this paper, and in order to make it computationally feasible, you say your time period is 1,000 years or something. Assuming that an asteroid is going to continue in the same direction for 1,000 years could start giving you a lot of complicating problems with your code. So I'm really interested in, and I know we probably don't have an answer here, but I'm interested in what the time step was in these sorts of calculations, how long it took them to run their code, and sort of how they put this simulation together.
Yeah, it's a great question. And you're absolutely right in your summary of things. I don't think they said, sadly, I'm looking at the paper to see if I missed it. The simulation ran for 10 million years total, but what their time step was in there, I don't know. It's probably fairly granular, perhaps on the order of tens of years. But I don't know.
10 million simulated years, by the way. They didn't leave the computer running from the Paleolithic era.
How did they figure out an accurate count model of the asteroids in the belt?
Oh, it's not accurate at all, at least as far as what I could tell. But they just populated 10,000 asteroids and were like, based off of this, we can guess with what more asteroids would do. And certainly there's more than 10,000 asteroids, but that's the maximum their computer could handle.
Yeah, exactly right.
So, yeah. And because they're all points, if you had 100 million asteroids, you just probably get a linear increase in the amount of impacts that happen. But I don't know. Maybe we should back up and discuss, I don't know, the paper as a whole and what sort of our takeaways from it were, or what the 40,000 foot look at this paper was.
Sure. Do you want me to finish sort of my run through on what they found, and then we can go back and give some interpretations?
Yeah, absolutely. Finish up.
Sounds good. Okay, so Nick is correct. They picked 10,000 asteroids as a round number and stuck them in orbits that are somewhat reasonable for the populations of asteroids they cared to study. There were 3 populations, so they weren't just looking at every asteroid. They wanted specific ones that have a reasonable chance of hitting the Earth. And in order to understand what these asteroids are all about, I just want to first explain the concept of resonance. Resonance is when 2 periods align. So this can happen under a variety of circumstances, but an analogy that just kind of comes to mind that I think people understand is if you're pushing someone on a swing. So you're pushing a kid on a swing, and you have to time your pushes to get the kid to go up right as the kid's at the bottom, just about to go back up again. And so you push at the right time, you're in resonance. If you pushed every other swing, it would still work, but it wouldn't be as powerful, but it's still resonance. But if you pushed when the kid were coming back toward you, you would actually take energy out of the swing and slow it down. You'd be out of resonance. So there are resonances in the solar system, and they're orbital resonances. So for example, there's a whole group of asteroids that orbits the sun twice for every 1 time that Jupiter orbits the sun. And this is a very stable orbit. Jupiter's gravity makes this a stable place to be. And so that was one of the populations they wanted to simulate. Then there's another population that's in resonance with Saturn, but this is actually an unstable resonance because it gradually moves them toward Mars, and then eventually they can get destabilized by making a close pass to Mars. So the authors were thinking, well, maybe Mars destabilized them and they come toward Earth. So that was what they were exploring. And then there's a third region that's totally chaotic. And they were thinking, well, maybe there's enough sort of random motion that some of those will make it toward Earth. So they did simulation runs of each of these different populations to see how many would collide with Earth. So in the case of the 2-to-1 resonance with Jupiter, it was only 0.02% of the asteroids that ended up crashing into Earth, which is not nearly enough to deliver 10 oceans of water. So not so good. The resonance with Saturn that is a little bit unstable and moves them toward Mars was actually much more effective. 1.9% of the asteroids crash into Earth in 10 million years, which doesn't seem like a lot, but 2% is actually a ton, because all it takes is having enough asteroids. If you get 2% of that, you could fill up the ocean. So that's a good result for them. And then those chaotic outer edge ones were also, like the Jupiter resonance, very low, far, far too low to be efficient to deliver water. They found one of these three groups, the Saturn resonance, could do it, could deliver water to Earth in significant amounts. But how much water depends on how much mass there was in the early asteroid belt that contained all the water locked in mineral form. And so here's a question. How much mass do you think is in the asteroid belt today?
What sort of units are we using here? Kilograms, hundreds of Earths?
Yeah, let's measure it in terms of Earth mass. So an Earth mass of material, a tenth of Earth's mass, 10 times Earth mass.
I'd guess maybe 5 times Earth's mass. What about you, India?
I'm gonna go 10.
Jamie, want to wager a guess?
Oh, shoot. Let's see. I'm going to go lower, actually. I'm going to say maybe it's between like half and 1 Earth mass.
Well, you're closest, Jamie, but not actually close at all. It's
shit.
1/5000th the mass of Earth.
Oh,
The asteroid
wow.
belt is not much stuff.
That's tiny.
Yeah. And even back in the day when things were still forming, it was only about 2 times the mass of the Earth. So it wasn't even that much long before the solar system looked like it did today. And so they make some estimates about how much water could be contained in the rock, how many rocks could be of certain size in this part of the solar system. And this is where things get a little hand wavy and we kind of brush over some details. And what they find is that it could be 8 oceans of water delivered to Earth via these collisions from this subgroup that it was in resonance with Saturn. So that's actually not that crazy. I mean, it doesn't give you 10. And if 10 is upper limit, well, that's not really possible. But 8 is still a lot of oceans of water and is in line with expectations of how much there might be in the mantle. So it's actually a pretty decent finding for this work, that this is not completely ridiculous.
you mentioned back in the day, the asteroid belt was larger. You say now it's 1/5000th. Before it might have been bigger. What are some reasons why it's smaller now?
Well, these asteroids crashed into things
Oh,
like the planets. Yeah.
makes sense.
Or the sun for that matter.
Asteroids actually like deorbit. I thought that took a lot of energy to like
It does.
deorbit an object.
It is, yes, it's incredibly energy intensive. So usually they have to have a close pass with a planet to do that, like Mars in this example, to lose energy and come toward Earth.
Do things get added? Does debris like get added to the asteroid belt, or is it just like a slow decay of things out of it?
Oh, is it growing or losing mass today?
Yeah.
Oh, yeah. I mean, not much either way, but that's a good question. It's probably losing more mass than it gains, but not very much, because everything that's left has been in stable orbits for billions of years. So it's pretty stable at this point. It'll be around until the end of the solar system.
But we don't like gain mass to the asteroid belt from, I don't know, outside the solar system or something like that.
Yeah, probably not from outside the solar system. The outer solar system could contribute mass to the asteroid belt, but that's a pretty unlikely circumstance.
So 40,000 feet, overview of this paper.
Mhm.
They wanted to find out, they've got this awesome premise, this first sentence in the paper, there are between 1 and 10 oceans of water on the planet, which first of all blew my mind. You think just one ocean of water, it's sitting there, but there could be just as much sitting below you, Jules Verne style. Well, not Jules Verne cavern with an ocean in it style. It turns out it's actually in rocks and mineral deposits, as you say.
Mhm.
But there is more water on the planet than we think should be there just by looking at other planets in the solar system. In order to figure out why they, or how it could get here, they investigate one of the possible ways water could have got here, which is asteroids being, or impacts coming to Earth delivering water. And to test whether or not that could deliver enough water, they run a computer simulation with all these variables thrown into it, and they find out in an optimistic space, the Earth could have received 8 times its current surface level of water, which fits into what the scientists think is the limit of water on Earth. And then they have a conclusion, which absolutely blows my mind, which is if we eventually find out Earth has more than 8 masses of water within it, 8 oceans of water within it, they use the terminology, that means Earth likely formed with the water or got it through some other means. So what are some of the other means that Earth could have gotten water, as opposed to these conventionally considered impacts?
Well, I think that was a really great summary. So thank you for offering that recap. Perfectly accurate. The paper does allude to some other theories, which I sort of mentioned earlier, that there could have been water that formed with the Earth. There could have been, this is a kind of a weird one, there could have been enough hydrogen around to bond with oxygen somehow and make H2O. I don't really know that I understand that theory so well, to be honest. I don't think the chemistry is all there, but it's a theory. I don't know. It's such a leading theory that everything came from elsewhere in the solar system, that it had to be delivered from elsewhere. So I don't think that really there are any good ideas of where else it could come from.
Okay, so it has to be delivery from elsewhere in the solar system, at least in the common scope of thought.
Yeah, I think the takeaway from this paper is that that is a totally plausible thing that could have happened, and not that it's possible it didn't. Though that's an accurate interpretation based on the most generous estimates of how much water is in the mantle, I don't think that's the major takeaway. That's not my major takeaway, I'll say.
Something they also brought up in the paper was that there's been meteorites, asteroid impacts on other planets, records of that, but or on the moon, for example, but they don't seem to have much water sitting around. Is the only
No.
reason because Earth is capable of maintaining an atmosphere, maintaining water, or what's the reason that a asteroid impact on Mars wouldn't eventually result in it having oceans?
Yeah, if Mars did have global oceans billions of years ago, they probably came the same way Earth's did. So yeah, in that case, Mars and Earth would have been similar evolution before they diverge. But why doesn't the moon have water then? It's a great question. And the simplest answer is because the moon has no atmosphere. There's no liquid water that can be stable on the moon. So even if these mineral water deliveries worked, the water couldn't seep into the ground. It couldn't recombine and interact with other types of rock and get subducted and stored deep underground. But that could happen on Earth because we have tectonic activity and because the Earth was pretty molten when this happened. So there was enough heat, enough forces to sort of drag the water down underground where it could become stored in the mantle. Also, the oceans could gradually leak water into the mantle. Leak is the wrong word. It's not dripping. It's being sort of captured and subducted, right? Locked into rock and pulled with tectonic activity with the magma underground until it reaches a point where it dissociates and becomes trapped in this rock form. But having liquid oceans is a big part of how we got the water into the mantle. Yeah.
Speaking of mineral water in rock form, is that wouldn't be stable at normal temperatures and pressures, or is temperature just a catalyst to get you into this stable rock form with mineral water? Yeah.
Could you get there under high pressure with low temperature?
No, I guess my question is, if we were able to drill down and get this mineral water out, this hardened water out, I know that's not the right term either, would it immediately turn back into some sort of liquid and some sort of mineral separate, or would it be stable at normal atmospheric pressure?
I think it would turn back into liquid and rock. Yeah, and I think it would happen really quickly. If we could drill down into the mantle, the moment that the pressure decreased in the local area we were trying to drill in, I think chemical reactions would happen really quickly. Yeah, these weird ones, wadstillite and ringwoodite, are definitely not stable anywhere near the surface. They are bizarre compounds that only form in the mantle. However, I was looking up what the highest pressure ever simulated in a laboratory is, and it is higher than the mantle. So in theory, it could be simulated. I would hope someone's tried to make these, but I'm not sure.
You can have the world's most unstable granite countertop.
Jeez.
So when we do our expeditions like to Mars where we're looking for water, was all of that like based on the same theory that we have on the Earth?
The efforts to look for water on Mars are both historical and current. So in large part, it's to explore whether or not there's evidence today that water definitely was on Mars billions of years ago, and in part to see how much water there might be. And so there was a lander, I want to say the Phoenix lander on Mars's North Pole, that specifically was looking for ice and did find a lot of ice. There is also some effort among the rovers on Mars to identify evidence of life in every possible form that could be stored in the rock. So you could have certain fossilized bacteria in the rock, might be underground, and that would be pretty huge. So there's a huge effort among the rovers as one of its primary missions to achieve that goal. I mean, if Mars had global oceans, it's very possible it had life, because life on Earth emerged pretty soon after we had global oceans and oxygen. Well, actually,
no, it formed before we had oxygen, because actually one of the reasons I was going to say that it seems unlikely that there could have been some kind of reaction between free hydrogen and oxygen to form the water is that there was not significant amounts of oxygen on Earth before there were little cyanobacteria that took sunlight and carbon dioxide and made oxygen, and then it was super toxic to everything that had evolved without oxygen.
Absolutely. Yeah, no, you're 100% right. There was no oxygen. So I don't really know that I understand that hydrogen theory very well.
I guess maybe they're saying there could have been a little, but I don't think, based off of my own like speculation, that would have been able to form oceans worth of water.
It doesn't really make sense. Well, so what do you all think about this paper? Do you buy it?
I find it a little disappointing that there isn't like an obvious disproving of delivery via impact. Like, I want there to be some obvious problem with the current impact theory. I don't know why. That's probably just a contrarian in me, but I want there to be like an upheaval. It makes sense that asteroids could deliver that sort of composition of water to Earth, particularly if the asteroids in the outer solar system are coming from farther out in the solar system, have a similar geologic composition to the Earth we see today. But I just want to see some obvious proof that, I don't know, something weird had to happen in order to get water. And unfortunately, that's not this.
Yep.
I find this a little too easy to buy. Sorry.
Yeah, I just feel like the idea of like the formation of the earth is hard to like wrap my head around personally. So the idea of like as it was forming, like things were also hitting it, which led to just like water in the mantle. It's hard to like conceptualize, but it's interesting. It's interesting to hear about.
I want to know where the water came from. Like, why do the asteroids have the water?
Oh, yeah. Presumably there's tons of hydrogen in the solar system, even after whichever supernova created the solar system we're in now. But oxygen has to be one of those chemicals only made well, all chemicals are only made in stars, or elements only made in stars. But I forget, is oxygen past the point where it only happens in supernovas, or does oxygen actually generate in normal star life cycles?
It does. It is generated by normal low mass. Actually, I don't want to say that. It's generated by normal stars, can be low or mid mass stars, but definitely higher mass stars.
So you have an explosion, you have presumably a ton of unburned hydrogen out there, and presumably a ton of oxygen somewhere, and eventually they come into contact.
The way that we assume the solar system formed, I believe, is to assume the abundance of material is the same as the solar abundance. And so based on the mass, age, properties of the sun, we know how much of different materials it should have, and how much of that it formed with, and how much of that it created. So I think we just assume a solar abundance is what everything started off with. And then it changed over time. The sun is creating in its core helium. Eventually it will create carbon and maybe some oxygen. And then there are processes on the planets that are forming from atoms into molecules. But yes, hydrogen is obviously the most common. There was plenty of atomic oxygen to start. Water is very common. It's just not common in liquid form, and it's just not common in the inner solar system. But most of the outer solar system, especially the small bodies, are ice. In fact, all of the giant planets had huge amounts of ice in their cores, in their center, outside the core somewhere. There's a lot of ice in there. It's trapped, but there's plenty of ice in the outer solar system. It's always been a transportation issue, is how could it possibly stably get to the inner solar system without turning into vapor and being lost?
You mentioned there that we assume the primordial star solar system is a pancake of material rotating
Yes.
around, orbiting around. Why do we assume it's a pancake and not a sphere?
Well, there's this fun saying in astronomy that everything is either a disk, a sphere, or a blob. It's not even that wrong. It's pretty accurate.
I personally identify as a blob.
Well, yeah, the reason is conservation of angular momentum. Angular momentum is rotational inertia. The things are rotating, they have to keep rotating. They don't just stop on their own. Like a top, it's going to keep spinning. Tops fall over, but in space, there's nothing to fall over. So it's just going to keep spinning. So if you take the blob, which is what it definitely started out with, and as the star starts to form, as our sun started to form, everything just got closer and closer together. So like a ballerina twirling in her arms, she's going to start spinning up, spinning faster and faster and faster. So that's how the disk started rotating. And then the things above and below just ended up falling down due to the gravity in the center. And so a disk is how it formed. Now that's sort of a theoretical approach. You could also take the empirical approach and look at forming planetary systems out there in the universe and say, well, what do they look like? Turns out they're all disks. So that's where the pancake comes from. They are indeed all out there.
And is that why when we look at the orbit of the planets, they're all vaguely going in the same or a similar plane? I think they're going in a similar plane.
Yes, it's called the ecliptic plane, and it is very flat. And they all go the same direction. And they almost all spin the same direction too.
I had a question that was kind of like based on how they created like the simulation, and like this is kind of basic, probably really quick to answer, but when they increase the like radius of the Earth, how are they able to do that and still like have an accurate result? Like that just to me felt like cheating. Like I don't know, like nothing hit, but we made it bigger and things hit.
Yeah, no, you make a great point. This is one of those details in the paper that I was a little bit disappointed in because they didn't explain it as well as they should have. What they did is in the two simulations that were not very successful, they did an initial run and found, oh, none of the asteroids hit Earth. And that's really bad for generating statistics because you can't extrapolate. Eventually, you would think one asteroid's going to hit Earth over a long enough time if there are enough of them, but out of 10,000, it's 0. So they made Earth 10 times bigger to make the target bigger. and see how many more would hit. And then they could extrapolate it down. Okay, so now we can actually do statistics with some number that's not zero. And then we could extrapolate that down. If the Earth were actually its actual size, how many would it be? And yeah, it would be far, far less than 1 out of 10,000. So that's why they did it. It's not a great, I don't love the approach because it requires them to make some assumptions about how the fraction should change based on the size of the Earth that I don't love. So it doesn't matter for their conclusions because all of the results are based off of the one of the 3 populations that actually was efficient at delivering asteroids to Earth. So the other 2 didn't really matter, but I agree with you. It's a bizarre way of doing it. And I would have said just run 1 million instead of 10,000 and see how many of those hit. I think that would have been a more robust way of doing it.
Because it's not only that it's just bigger and thus a larger surface to hit, like it would also change all their gravity calculations, I would assume. Or did they like make it the same amount of mass, but just bigger?
Yeah, no, you're right. It would change a lot of things. I don't know. I don't know that they mentioned anything about the mass changing, just the radius.
I assumed because they didn't mention a mass change, I assumed they were just ballooning out the Earth, making it a bigger target and not changing the mass, but that's
Yeah.
definitely something they could have clarified. I also found it interesting that they brought up that they had something like 2% delivery in their optimistic scenario. Their V6 resonance, they called it, over 10 million years. And they cited another scientific paper which was able to get a 3% delivery over some period of time. I'm not entirely sure what, but that goes to show that there's like, even with these computer models, there's a big amount of variance that you can get. And I guess 1% difference isn't that much, but in order to really understand how these models are working and how accurate they are, there's really just so much more digging into it that I would like to do than this paper provided.
Yeah, this is astronomy, so factors of 2 are not important. Factors of 1.5 are even less important. 2 and 3 are the same.
But I think that is a good point about all of this is dependent on how they set their parameters and how they like ran their code and how they like you could imagine changing the outcome drastically by setting a couple of parameters differently.
Yeah, I think a worthwhile effort would have been to explore how much changing some of those initial assumptions could impact the results.
How much of a reproducibility problem is there in astronomy? I know that in the like biological sciences, it's a huge, huge issue that there's all these efforts to address, but how much of an issue is it in your field?
I don't know that anyone's made an effort to quantify it. I remember hearing about a great study years ago from, I think it was psychology, that found a very low percent reproducibility in that field. I think it is an issue. I think it is an issue for sure. Here's a good example. It's actually somewhat of a hot topic. A year and a half ago, there was a major discovery in the clouds of Venus using spectra. So this is looking at all wavelengths of light coming from the clouds of Venus to see what elements they were producing known patterns of emissions, and found a detection of a rare chemical called phosphine. Phosphine on Earth is only produced by organic processes. Bacteria in the dirt basically produce phosphine. So a detection in the clouds of Venus was huge. This made Nature, this was a pivotal discovery and has spurred a ton of interest in Venus. So great. The original group was able to reproduce their results with new observations. No other group has been able to reproduce it. There are a lot of interesting choices in methodology, filtering out the data to get the signal behind, and it seems like certain choices can either leave the detection in or take it out. So there's a lot of dubiousness about whether or not that's real. It's a reproducibility issue, but it's also a methodology issue. The good news about Venus, though, is NASA just approved 2 missions to Venus, and ESA, the European Space Agency, just approved one of their own. So 3 new missions are going to Venus. So it's going to be a great decade for Venus studies coming up.
Oh, I had a question from the paper. Something that they asserted in the paper was that the smaller planets formed substantially after the larger planets like Jupiter, Saturn, that sort of thing. Why do we believe that's the case?
Where did you see that in the paper? I don't recall seeing that. It's an interesting point.
Says the late stages of terrestrial planet formation are thought to occur after the giant planets have formed, and then a bunch of citations.
It depends on how you define formation. And I think when they say late stages, what they mean is formation of the atmosphere and the volatiles, which are the non-popular chemicals that mostly are on the surface or in the air. And it's believed that, as I said at one point, all the planets formed with the same initial distribution of stuff because they were close together. They all formed from the same pancake of dust and gas. They couldn't have been that much different. But because they all had different masses and different proximity to the sun, things started to evolve very early on. So initially there would have been like hydrogen around Earth, a big puffy cloud of hydrogen, but hydrogen is so light that Earth can't hold it. So it would just kind of drift up in the atmosphere and get blown away into space by the sun, but it would get lost. And so the atmosphere that we now have came later on. So it came toward the end. It was one of the last things in the solar system to form because the Earth had to be cool enough where the atmosphere would stick around and different types of chemicals had to kind of come out of the rocks and emerge. Some were delivered, and that's how the late stages would have occurred. So I think the point in this part of the paper is to say that the giant planets preserve their primordial atmospheres. They all still have the hydrogen and helium they formed with. The interior planets lost that and had this secondary round that is the late stages of the formation. That's my best guess at what they're saying here.
Well, then I think that'll do it. The last thing I want to do is if any of you have any sort of social media or other projects that you're working on that you'd like to direct people towards. We'll start with you, Will, since I know that you co-host another podcast and have some other projects going on.
Yeah, so my podcast is called Astro Soundbites, and it is a spinoff of the popular astronomy website astrobites.org, which is entirely run by grad students. In each episode of Astro Soundbites, we pick a theme and discuss new research around that theme. Each episode includes a space sound that we like to discuss, and then we have a lighthearted and sometimes philosophical discussion like we had here today. Astro Soundbites is not always in plain English, I will say, but if you like space, you would get something out of our show. So you can find us on our website, astrosoundbites.com, or anywhere you find podcasts.
Great. Yeah, make sure you go check that out if you liked this episode. And India, do you have anything you'd like to plug, social media, any other projects?
No projects over here.
How about you, Nick?
No, nothing I'd like to disclose due to NDA agreements, but I'd like to thank both of you guys for sharing this information with me. And I appreciate having me on this podcast. And I'm going to go immediately back to my corporate overlords at Nestle and tell them about this amazing source of water that they can start mining.
Oh no. Oh no. Well, thank you all for joining me on this 4th episode of In Plain English. We've been discussing the paper, How Much Water Was Delivered from the Asteroid Belt to Earth After Its Formation, with our expert Will Saunders and our guests India Bland and Nick Wohlslegel. You can download the paper for free on our website at inplainenglishpod.org. And once again, you can follow us on Twitter at Plain English Sci. That's PLAINENGLISHSCI, or find us on Facebook at facebook.com/plainenglishsci. And you can find our podcasts on Google Podcasts, Spotify, SoundCloud, or wherever you listen to your podcasts. We'll see you next time for another paper presented in plain English.